And we will see most of you, I hope, in September. We're starting again September 9th with a talk by David Wallace, who will be the first speaker at the center next year. Some of the announcements I wanted to make nonetheless. We are going to have a conference in October in the philosophy of neuroscience about the population doctrine in neuroscience. And there's a call for papers. The deadline is June 15th. So if you're online and listening to this lecture and are interested in that conference, please submit an abstract for the conference. The details are on the center's website. Also, since it's already time to do that, we welcome applications to the center for fellowships for a semester or a year. The deadline will be in December, but it's not too early to start advertising it. So please have a look at the website and join us for a semester or a year. All right, today it's my great pleasure to introduce our friend and colleague, Glymour, who really does not need any introduction, but I will do my duties. I will just. You are going to have one, whether you like it or not. But I will change the content. We'll be much less friendly now.
It's nice to have a circumstance where you have to be committed.
So anyway, Clark is alumni university professor emeritus in the Department of Philosophy at this small university near us called Carnegie Mellon University. He's also a senior research scientist at the Florida Institute for Human and Machine Cognition. He's a Guggenheim Fellow, he's a fellow of the statistics section of the AAAS, and so on and so forth. He has written many very influential books, starting in 1980 with a book called Theory and Evidence, that is a classics in philosophy of science that many of us have read. Maybe his most influential book, even so I haven't really looked, by looking at Google Scholar, is Causation, Prediction, and Search, which I assume because it reached way beyond philosophy and has changed some of the way we're thinking about causal inference, has had an enormous impact. I'm very fond of BaseNet and graphical causal models in psychology, which I've read very, very carefully. And he's published many other books, but I won't go through all of them today. He's extremely well known for his work on causal inference and causal learning, which in a sense has changed the way we all think about causation since basically the 1990s. So thanks for coming and for closing. For closing the sentence.
Glad to have you in this circumstance.
And today, Clark will be talking about Reichenbach and the direction of time. Clark, those yours.
So I don't know whether to apologize or not, but this is kind of a sentimental. And you'll see why right from the beginning. So I beg your indulgence. So it's about 4 people. Me, Cynthia Schuster, whom only one of you knows of, Wesley Salmon, and Hans Reichenbach. And it's about me. After I was evicted from the University of Montana in 1962, I went to the University of New Mexico, which had perhaps the worst philosophy department on earth, run by a man named Archie Baum, who some of you may remember as the editor of the Directory of American Philosophers, now defunct, which used to come out every year or so. Archie ran the philosophy department in New Mexico, and his shtick was that the world runs on dialectic, organicity, and polarity, and I couldn't fathom a word of it. So I decided to major in chemistry, with the result that I spent the year of 1965 trying to make a molybdenum sandwich compound with a whole wall of test tubes that looked much like that, night after night, and it was really boring. So what do? Well, I got a book out of the library. And I read it. And the book was The Direction of Time. And reading the book changed my life because I thought, gee, this is the kind of philosophy maybe I could do. So Cynthia Schuster had been my undergraduate teacher and confidant for the 2 years I spent at the University of Montana. She was a wonderful woman. She was fired from Washington State University for inviting Oppenheimer to campus to speak, which may be an omen of our times. I had a terrible undergraduate record, but wonderful relations with Cynthia. And when I decided I had to leave chemistry, she persuaded Wes Salmon, whom you do know, to admit me. And there I went. And I will say, Wes was perhaps the most morally insightful supervisor, or indeed colleague, I ever had. I'll spare you that story. They were two of the three doctoral students of Hans Reichenbach. There was a third. Nobody seems to know who that was or what became of the person, but they were two, they were close friends. And so Cynthia succeeded in persuading Wes to take a flyer on me, despite my rather troubled academic record. Let me talk about Reichenbach a little bit. Reichenbach was associated with the most detested scientist in Nazi Germany, and that was, you guessed it, Albert Einstein, who's already in bad odor because he had written a letter against World War I, along with many other artists and intellectuals in Germany at the time. Reichenbach went to Turkey. He went to Turkey because Ataturk, Mustafa Kemal, was maybe the smartest man in Europe. Ataturk, who had essentially determined to remove the Ottoman tradition in Turkey with various ingenious moves, realized that Hitler had created an opportunity. And so he created a new university and hosted as many intellectuals fleeing the continent as he could bring to his new university. Hans Reichenbach was amongst them. Now, Ataturk knew that while he could get people who were fleeing Germany because they were desperate, have a hard time keeping them. So the contracts he made with his immigrant scholars were clever. They were repeating contracts for 5 years. They automatically repeated. You could not resign the contract. You could not leave the country if you were employed. And you had 1 week between the end of one contract and the beginning of the next to leave the country. So Reichenbach tried in vain to get out, and finally some friends at UCLA got the timing just right, and he moved to the United States. Now, he didn't do well on the way. He had a heart attack while trying to be a mountain climber in Switzerland. And so when he made it to UCLA, he spent a good deal of time not working, but that was doubly determined almost, well, no, because he was a German citizen, World War II was going on, he spent the war under house arrest. He was allowed to leave for medical purposes and to give lectures at UCLA, and that was it. he was, in my assessment, a man of extraordinary aperçu. He had insights. And in my view, that's 1/3 of philosophy. The other 2/3 are mathematics and religion. He had the first and the third. His mathematical skills were really quite limited. He knew the kind of mathematics you needed for physics, which is what he had studied, but it wasn't the kind of mathematics he needed for his efforts at the direction of time. The remarkable and sad thing, actually, in looking back, is that Reichenbach was intellectually isolated at UCLA. In his work on the direction of time, he really needed help, and he didn't have it. His theory of probability, big book he really began in the 30s and finished when he was at UCLA. He was aided in its mathematical parts by Valentine Bargmann. Bargmann had been a friend in Germany. He had come to America and become Einstein's assistant, and he continued to help Reichenbach, at least by letter. I met Bargmann, and I didn't have the wit to ask him how much of the theory of probability he wrote. Another reason I would like a time machine. So, Direction of Time was written after World War II. I think almost entirely when Reichenbach was in Los Angeles, and it was not finished. It was undone when he died. His wife, Maria Reichenbach, sort of edited it and brought it to publication. I think the book is inspired by several dimensions of Reichenbach's thought. One is his long-standing concern, beginning with his doctoral thesis, with probability. His doctoral thesis is on probability. He had thought about directed graphs and their relation with causal relations because he thought about the structure of the topological structure of relativity. And I think he transferred that. And something else which set him apart from the entire group of logical positivists or logical empiricists we think of at the time, Reichenbach, in my view, uniquely was committed to the existence of systematic methods for discovering causes from observation. That's a long glass.
It's in the front.
Yeah.
What glasses do I need?
Right behind the computer.
Oh, thank you so much. Would you like to give the rest of the lecture? I have advice for you. You may get to 82. Skip it, go directly to 83. You gotta be better. So that's what I think are the informative influences on this book. Now, connections between causality and probability have been in the statistical literature for at least 60 years before The Direction of Time was published. They had been used since the late 19th century in the statistical method of linear regression. They had been used since early in the 20th century in factor analysis. And during World War II, the economists, mostly those associated with the Cowles Commission, spent a great deal of effort trying to understand linear causal models. There's not a shred of evidence I can find that Reichenbach knew any of this. He seemed almost completely innocent of what was going on in statistics at the time, and in psychology, the only interest I've really found was in psychoanalysis. He gave lectures at the Los Angeles Psychoanalytic Association. How serious his interest was, I don't know. Now, forgive the cliche, the direction of time had been anticipated by Reichenbach himself. In 1925, he wrote an essay called The Causal Structure of the World. And he attempted to obtain direction of time from causal relations and probabilities, always under the assumption that causes precede their effects and that time is acyclic. In that work, he credits both Lewin and Carnap, who had thought about the topic some, in works long since forgotten. Kurt Lewin, Carnap, name you know. Kurt Lewin, you may not know. Lewin was a colleague in Germany, and I think he wound up at the University of Iowa and mostly worked on psychological matters. In 1925, Reichenbach used his probability logic, which I won't go into detail, but it is a complete mess from a formal point of view. It doesn't even satisfy the axioms of finite frequencies. There, he tried to get time direction from what he called the topology of probability. That's a quote, at least in the English translation. And he has these two forks, the pointed fork and the saddle fork. Now, unfortunately, he doesn't put any arrows on his diagram, but I assume the pointed fork points towards C and the saddle fork points away from C. But that's just me. And he has these claims. So the A with the funny arrow means if A occurs, then with probability, B occurs. Not how much probability, but some probability. Yes, or other vague thing. And here we have properties of the pointed fork, A and B with some probability bring about C, and C with some probability returns the favor and brings about A and B and so forth. The bars mean not. So if A and B, in this example, A and B with some probability bring about C, but A alone doesn't, C alone doesn't. B alone, sorry, C with some probability bring about A and B, but A and B alone don't with some probability bring about C. And here we have the reverse relations, oddly enough. If there is a saddle fork, then A with some probability brings about C. I take it the idea is that if C is the cause of A, then if A occurs, C must have occurred with some probability. So any of you who know the later discussions of Reichenbach's conjunctive forks and so forth will see an anticipation in this work. So after World War II, Reichenbach reconsidered the very same problem, but now he had a lever, the principle of the common cause. And that made some things better and some things dramatically worse, partly because of another aperture, which I will get to. So principle of the common cause is often attributed to the direction of time, but actually is stated quite clearly and explicitly in 1938 in Experience and Prediction. more than a decade before the book I'm principally talking about. So, principle of the common cause is that statistical associations are usually, Reichenbach allows there could be anomalous exceptions, produced by a common cause. Now, Reichenbach formulates it that way, but he realizes that's dumb. Why? Well, because two kinds of events could be associated in probability without having a common cause, because one causes the other. So he reformulates it in the direction of time as statistical associations between two types of simultaneous events. So he can get rid of that possibility of a unconfounded causal relation. Now, in experience and prediction, he sees the principle as a tool for discovery. And he gives a kind of charming example. He imagines a man in a kind of box. He even gives a man a name. He calls him Copernicus because he's in the business of discovery. And Copernicus sees, apparently simultaneously, a bunch of shadows of birds on the walls of his box. It's a funny kind of box where you can, it's more like sheets. Yes. And Copernicus uses the principle of the common cause to infer, and of course, since Reichenbach is making up the story, to infer correctly that there is a single common cause of these shadows, namely a real bird. And that's roughly his, well, what's the right word? Or a trope. A symbol like this. Is it a simile, an analogy? His model. Yeah, that's the word of the day. His model for how we infer an objective world from our sense of perception. So Reichenbach is sometimes given the authorship of a distinction between context of discovery and context of justification. It wasn't original with him, but he does have such a distinction. But he doesn't think that that distinction means the way you discover something isn't evidence for what is discovered. In fact, he says explicitly it would be foolish to disregard how a hypothesis will come to when assessing the warrants for it. So the principle of the common cause has been used, applied many times before Reichenbach articulates it. It is the governing idea of late 19th century neuropsychology, the so-called diagram makers, who tried to infer the causal relations amongst hypothetical causal factors in the brain from patterns of disabilities, incapacities. And of course, Leon Thurstone's factor analysis. Now, I cite Thurstone kind of unfairly because Thurstone was a man of his time. And his time was a time when people didn't talk about causality, just as they didn't talk about sex. It was verboten. And his book, Thurstone's book, The Factors of Mind, sounds like it's a book about causality, but in fact, right at the beginning, he says it's about linear reduction of data, nothing else. So although Clearstone's work was widely taken to be a tool for causal inference. It was publicly disavowed by its author as serving that purpose. In any case, Reichenbach knew none of this. So on to the direction of time. There are 4 parts to this book. The first part is time order without direction from locally simultaneous observations. Reichenbach is always concerned not with the metaphysics so much as with a kind of wild generalization of epistemology. So there is next a section on the direction of time from thermodynamics, which is really attributes the direction of time to increases in entropy in isolated systems and is essentially an entirely derivative effort. I should mention a lot of Reichenbach's work was not entirely, but largely derivative. So his philosophy of space and time reads right out of Helmholtz, whom he must have read very carefully. His doctoral thesis is just work by Poincaré, which Reichenbach put into a Kantian setting, because all those guys wrote Kantian doctoral theses. Bertrand Russell did, Carnap did, Reichenbach did. The third section, which is the one I'm going to talk about, is the direction of time from macroscopic causality. And the fourth section is on the direction of time in quantum theory. I don't know anybody who's ever read it, and I haven't. So if you ask me about it, good luck. So here's the strategy. Causes precede time, causes precede effects in time. Locally, simultaneous versus non-simultaneous events are empirically ascertainable. Then, and this is the part I find interesting, assumptions relating directed acyclic graphs representing causal relations with probabilities. And finally, using these premises to infer causal directions and from that time direction. So that's basically the logic of the book, except for the thermodynamics part and the quantum mechanics part. So Reichenbach claims that from classical physics, which allows time reversibility and observation, local observation, we can determine whether one event is causally between another. And the problem is then to determine, if you think of this as a graphical representation of a set of causal relations, possible set of causal relations, to determine which way the edges go. So this is a little complex to say, but here's the conclusion he draws about what's locally observable. Maybe I best go to the next slide. He says, he does it in terms of bouncing balls, which is quite confusing. But basically, he says, we can determine from local, almost simultaneous observation, yes, whether events E and C are the causes of A, or A is the cause of E and C. Yes, that's a disjunctive. All we determine is the disjunction, not the disjuncts. As against, E is a cause of A is a cause of C, disjunction, C is a cause of A, and A is a cause of E. So we have two alternative disjunctive hypotheses, and for any one of these triples, we can, in principle, determine which pair of disjuncts obtains. Either or else, or, right? I can't be more vivid than that. So this is more. This is how he thinks he can determine that, but let that be. I'll skip the bouncing balls. And Reichenbach has a little theorem. He doesn't prove it. He proves nothing in this book. In fact, Wes Salmon had to prove some of the claims Reichenbach made because he doesn't prove anything, but some of what he says is true. And he says, with something I said, happens a lot. So he says, look, if you've got one of these triples, yes, undirected edges, right? And you've got a whole network of events, all the events in the universe. And you've got these triples, yes? And it's not a complete graph. It's not that every event is in a triple with every other event, but there's always a pathway from any one event to any other, yes? Says, look, given this principle, yeah, that for any triple, I can determine, I can know whether it's or alternatively, yeah, I can know which of those disjunction obtains. If I know the direction of a single edge, the whole graph is oriented. And he's right. That's one of the few things that is right, but that's okay. Reichenbach has, as a kind of first principle connecting causation and probability, that two events, and when I say events, I mean event types because Reichenbach is a frequentist. Two events are going to be made independent, conditional on any set of mediators of every causal pathway between them. So here, y1, y2, and y3 are the mediators between x and z. And if you condition on the occurrence or absence of all three of these guys, then x and z are independent. Now we come to the heart of the discussion, which is actually troubles. The notion of conjunctive force. So here is Reichenbach's formal set of conditions for what he calls a conjunctive fork. And you will notice that I have depicted his depictions, this is right out of the book. Conjunctive fork can be either what he previously called a pointed fork or a saddle fork. It can go from C to A and B as in a common cause, or from A and B to C as a common effect. And he thinks both of them can be conjunctive forks. The one on the left is almost the only structure that has been discussed in modern literature as a conjunctive fork, not the one on the right, which is a kind of causal structure now routinely called a collider in statistics. Now it really gets weird. So I put this up just to prove to you that I'm not making up what I'm about to say. These are Reichenbach's words, but it's never easy to, so I'll just tell you. Reichenbach says Both of these structures can occur in nature. But the one on the right is a problem. Why is the one on the right a problem? Well, the collider principle is that two independent causes of a third variable are dependent, conditional on their common effect. Anybody know who first proposed that? Who first recognized that fact? It was Sewell Wright in 1921. It's usually attributed to a psychologist in the 1960s, which is an example of Stigler's law, which is that nothing is named after the person who actually discovered it, at least in statistics, and I suspect also in some other subjects. So look here. Reichenbach, excuse me, clearly coffee time. Reichenbach recognizes that if he conditions on C, A and B are dependent. Yes? Which is to say, yeah, there's a probability distribution, a real probability distribution, as it were, in the world, in which two events have no causal connection with one another, but they are associated to events of n types. Well, principle of the common cause says you know how to turn that off. Oh, yeah.
The sun.
It's my son. Believe it or not.
Bruce.
Yeah, Bruce, yeah. Yes. The largest philosopher in Kansas.
True.
At any rate, he's got a problem. The principle of the common cause conflicts with what he's discovered about conditioning on common effects. So how does he solve this problem? Well, let me put it to you. What would you do? You've got this principle. You're really committed to this principle. You've got this insight, an aperçu. You really see it. You believe the phenomenon. He does what many people do. I could give you examples of statisticians who have done the very same thing. This is what he does. He says, it can't possibly happen. It can't happen that that occurs by itself. Now, not that two events can't be causes of the third, but if it happens, there has to be another common cause. Now, it is unclear to me whether Reichenbach, reading text, I'm not sure, whether Reichenbach thought this was a limitation on God, or whether it was a kind of Kantian limitation on reason. But at any rate, we don't have to worry about the conflict between the principle of the common cause and colliders, because it can't happen. You look skeptical. You look skeptical. You're skeptical of me or Reichenbach? Well, wisely both. But in this case, I'm telling the truth. So this is really the point of my story. In in summary, Reichenbach is the first systematic effort to relate causal relations and probabilities. In the end, he recognizes that conditioning on what are now called unshielded colliders, that is to say, colliders where there's no causal relation between the causes, conditioning on the effects in unshielded colliders can make the causes dependent. He recognizes it conflicts with the principle of the common cause, and his solution is it's impossible. This is a long tradition, and I mean, what better? And this is good. If I can't deal with it, it's impossible. Entirely an aside, I once, with my colleagues, did a simulation of a method widely used in psychometrics, and showed that when there was a direct effect between two variables and also an unmeasured common cause, it was just garbage. Now, this is, of course, the standard worry in experimental design, yes? You're worried about confounding direct effects with common causes. Well, the statistician who was the author of the program didn't dispute my simulations, but he wrote me that this could never possibly occur in nature. Reichenbach's spirit lives on. And in a way, it's kind of sad. So, I'll leave that be, it's obvious. Now, in a way, it's all kind of a pity because Hartree Field, you may know him from his book, Science Without Numbers, or from other perceptive essays. Hartree is full of aperçus. Pointed out, I've forgotten the title of the essay, but basically, you could use the principles of connecting graphical structure and conditional independence that were used in the PC algorithm developed years ago, decades ago, by Peter Sperdes and myself, to ideally apply it to undirected graphs. And if there were unshielded colliders, you could orient everything. And that brings me to my afterwards. So there is a body of work that is abstractly, intellectually indebted to Reichenbach. It carries out his program, but none of it ever cites Reichenbach. That's a bit unfair. And it is all about work elaborating connections between directed graphs representing causal relations and probability distributions. It is literally an extension of the ideas in the direction of time without recognizing any influence there. It starts with Caverian Speed around 1980, who recognized what we now call the Markov condition, which is that in acyclic causal relations, effects are independent of their non-effects, stuff they don't affect, conditional on their direct causes. And that was generalized by Judea Pearl and his graduate students in the late 80s into an algorithm which captures that very idea quite efficiently. It's called D-separation. I'm sorry, there isn't a better name. And then Peter and I used the Markov condition and D-separation to kind of realize Reichenbach's ambition for a logic of discovery using his principles in what's called the PC algorithm, our initials because we were so modest. So actually, those ideas have worked out in Reichenbach's ideas really are really worked out in the PC algorithm. He should have been cited all over the place, but shame on me, he wasn't. But I have bigger things to be ashamed of, so. And Reichenbach's ideas about a method of discovery, basically using the principle of the common cause, and his elaborations, and the collider principle, all of which are kind of incoherently in the direction of time, turns out to be an actually fruitful search method. So I will give you one example, which I thought was preposterous when I read it, but it turns out it's true. It's been repeated several times by independent groups with independent data. So the PC algorithm just uses conditional independence relations in a systematic way to identify causal graphs. Graphs which encode conditional independence relations and which are, if you want, and we want, interpreted as causal claims. So it's a correct algorithm in the sense that you can prove it's, in the statistician sense, consistent. That is to say, if your sample size increases without bound, you converge to the truth. But it's a lousy algorithm. I mean, there are much, much better algorithms since, what was it, 1991 when it was introduced. I mean, lots and lots and lots of much better stuff. But a few years ago, a group, principally at the ETH in Switzerland, not incidentally, Einstein School and my grandfather's school. My grandfather went to school with Einstein. I went to school with Evel Knievel. Social mobility, American stuff. Too much revealing.
You called it, you're aware, right?
So here's what these people did. So you guys all know the basics of biology. You've got your DNA. It transcribes into messenger RNA, and the messenger RNA then gets hooked up to some structure in the cell, which stitches together amino acids to make proteins. Yep. So the DNA expression is a cause of phenotypes produced by the protein. So here's the question. Lots of genes, lots of phenotypes. Pick a phenotype you can readily measure. Can you determine, can you find some of the genes that control that phenotype without manipulating the genes? You can find it just from the frequency data of the phenotype and something about the genes you can measure, and messenger RNA you can measure. You can measure its concentrations. The technology's gotten better and better. So this is a kind of Reichenbachian problem. These people had 47 cases for a plant. Very common plant. Never mind the name because it's Latin and I don't do dead languages. So they have 47 cases. For each of these cases, they've got the entire messenger RNA profile. 20,000 genes. Lost actually. And they have the time from germination to flowering for each of their 47 plants. That's it. 20,000 variables. They applied what I will call Reichenbach's method, the PC algorithm, and they essentially ranked the genes. They took the top ranking for which they could do knockout experiments to test the prediction. And of their predictions, they found 4 known genes, which had been found independently by laboratory work, and 5 novel genes, which were shown to be regulators by the knockout experiments. And you might ask, well, what about the other? There were some others in their top ranking. Those knockout experiments all killed the plants. So I count that as quite remarkable vindication of Reichenbach's ideas. And I will stop with some thanks to 2 people who aren't here, to my regret, Cynthia Schuster, Wesley Salmon, and a third one who very much isn't here, Hans Reichenbach. Thanks very much.
We take a 2-minute break and then we'll have time for questions.